You ever looked at a massive steel ship and wondered, how on earth does that float when a tiny little pebble just sinks? Or how does an airplane wing create enough lift to carry hundreds of people with nothing but air around it? Well, you are in exactly the right place. Today, we are diving into the amazing world of fluids, both when they are still and when they are in motion. And by the end of this, you're going to have a rock-solid grasp of the key principles you need for your physics exams. Let's dive right in. Okay, so let's really tackle that first question. It's a classic physics puzzle for a very good reason. How can something so incredibly heavy, made of a material that we know sinks, just float so easily, while a simple little rock just plummets straight to the bottom? The answer to this, it's all about pressure, density, and displacement, and it lies in the physics we're about to unpack. So, here's a quick roadmap for where we're headed. We're going to start with the absolute basics. What makes a fluid? Well, a fluid. Then we'll uncover the secrets of still fluids before jumping into the powerful world of fluids in motion. We'll even tackle a real exam question to put your new knowledge to the test, and then we'll wrap it all up with a quick final review. Alright, let's get into our first section. Before we can even begin to understand why ships float or planes fly, we have to get right to the heart of it. What is a fluid really? It's actually pretty simple. A fluid is just any substance that can flow and change its shape to fit its container. So we're not just talking about liquids like water or oil here. This also includes gases like the air we're breathing right now. It's a really broad and absolutely essential category in physics. Okay, so now we know what fluids are. Let's explore what's going on when they are just sitting still. This is the world of hydrostatics, the science of fluids at rest. And believe me, this is where things start to get really, really interesting. First things first, let's talk about density, which we represent with the Greek letter rho. Just think of it as how much stuff, mass, is packed into a certain amount of space or volume. This one simple property is the reason oil, which is less dense, just floats right on top of water. It's a super fundamental concept that really dictates a lot about how fluids behave. Next up, we have pressure. In a fluid, pressure is the force it pushes on a surface, and it gets stronger and stronger the deeper you go. The formula for this is P equals rho GH. That's density times the acceleration due to gravity times the depth. This is exactly why deep-sea diving suits have to be unbelievably tough to handle that crushing pressure at the ocean floor. This leads us to a really cool idea, Pascal's Principle. What it says is that if you apply pressure to a fluid that's in a closed container, that pressure gets sent out equally in all directions. And this isn't just some abstract theory, it's the magic behind hydraulic systems, like the brakes in your car or a heavy-duty hydraulic jack. A tiny little push can create a massive force. And that brings us to the star of the show, Archimedes Principle. This right here is the key to solving our whole floating ship mystery. It tells us that any object put into a fluid gets an upward push. We call it a buoyant force, and that push is exactly equal to the weight of the fluid it moved out of the way. So, how do we figure out how strong that push is? Well, it all comes down to this simple but super powerful formula. The upthrust, or buoyant force, is just the density of the fluid multiplied by the volume of fluid the object displaced times gravity. So if this upward force is stronger than the object's own weight, it floats. If it's weaker, it sinks. It really is as simple as that. And you can see this principle everywhere in the real world. A ship floats because its massive hollow shape pushes aside a huge amount of water. That creates enough buoyant force to hold up all that weight. And submarines, they are masters of this. They use special ballast tanks to change their density letting them dive or surface whenever they want. Okay, so we've got a good handle on still fluids, but what happens when they start to move? It's time to shift gears and dive into the exciting world of hydrodynamics, the physics of fluids in motion. So, when fluids are on the move, they usually flow in one of two ways. You've got streamline flow, which is also called laminar flow. It's smooth, it's orderly, kind of like a gently flowing river. And then you have turbulent flow, which is the total opposite. It's chaotic, messy, full of swelling eddies. Think of water crashing against rocks. Now, the equation of continuity is a really powerful idea that's all about conserving mass. It basically tells us that when a fluid is flowing through a pipe, if that pipe gets narrower, the fluid has to speed up. Why? To get the same amount of fluid through in the same amount of time. It's exactly what happens when you put your thumb over the end of a garden hose to make the water spray out faster. And now we get to another giant of fluid dynamics, Bernoulli's Principle. At its heart, it's all about conservation of energy for a moving fluid. It says that if you add up a fluid's pressure, its kinetic energy from moving, and its potential energy from its height, that total sum stays constant all along its path. So what's the big takeaway from Bernoulli's Principle? It's this simple but powerful idea that where the speed of a fluid is high, its pressure is low, and the other way around. This simple inverse relationship is exactly how an airplane wing generates lift. The air has to travel faster over the curved top of the wing, and that creates a pocket of lower pressure that literally pushes the wing up from below. Amazing, right? Lastly, let's touch on viscosity. The easiest way to think about it is as a fluid's internal friction, or even simpler, just its thickness. So syrup is super viscous, it resists flowing. Water, on the other hand, has a very low viscosity. This property is absolutely critical for things like engine lubricants, which need to be thick enough to stick to parts and keep them from grinding against each other. Okay, we've gone through a lot of theory. Now it's time to put it all to the test. Let's see how these principles actually show up in real exam questions so you know exactly what to look out for when the time comes. Alright, take a look at this. It's a real question from a past WAEC exam. It asks for the correct statement about Archimedes' Principle. What do you think? Is the upthrust on a body a measure of the mass of the fluid displaced, the weight of the body, the volume of the body, or the weight of the fluid displaced? Go ahead and pause here for a second and really think it over. Okay? You ready? Let's break it down. Step 1. Just recall the definition we talked about. Archimedes' Principle literally says that upthrust equals the weight of the displaced fluid. Step 2. We have to remember that weight is a force. It's not the same as mass or volume. That immediately rules out options A and C. So what are we left with? The correct answer has to be D. And this slide right here highlights a super common trap students fall into: confusing mass with weight. You've got to remember, weight is the force of gravity acting on a mass. In physics, and especially on your exams, you should always be thinking in terms of forces. This one little tip can save you a whole lot of points. We are just about at the finish line. Let's wrap things up with a quick final review to make sure all these key ideas are locked in and fresh in your mind. Think of this summary table as your ultimate cheat sheet for revision. It lays out the 4 big principles we've covered: hydrostatic pressure, Archimedes' Principle, Bernoulli's Principle, and viscosity. You've got the core formulas and a key real-world application for each. Everything from the bottom of the ocean to high up in the sky. Seriously, keep this handy for your final prep. It's a gold mine. And finally, here are a few top tips to help you crush those exams. Be meticulous. Always include your units and label your diagrams.
Pay attention to the instructions, like which value of G to use. Show all your work for calculations and practice under timed conditions. You've got the knowledge now. Go out there and show them what you can do. Great job following along. If you found this tutorial helpful, don't forget to subscribe to our YouTube channel for more easy-to-understand lessons. And hey, want to practice more questions and get step-by-step solutions? Visit examkp.com right now and keep learning.